All right, so I want to talk more about invertible functions because I feel like I didn't do them justice. For example, I didn't say what the actual mathematical definition of inverse functions are. So we say f and g are inverses of each other, or inverse functions, if exactly this condition, f of g of x is equal to x, or similarly, g of f of x is equal to x. And if you think of functions as performing a task, doing an algorithm, performing a computation, something like that, then inverse functions undo each other. So kind of a classic example from a much more advanced math called abstract algebra. Suppose I put on socks, and then I put on shoes. The inverse of this, so this is me performing the function f. F inverse would be I take off my shoes, and then I take off, I guess I'll say then I take off my socks. Okay, and this will always be the case. So let's see it happen in mathematics. So suppose f of x is x cubed minus 7. Then what does f do? F cubes x, then subtracts 7. Okay. Now, if we were to do the opposite actions in the opposite order, we would have to first add 7, then take the cube root. So let's build that function. So g of x, the first thing it will do is add 7 to the input, then it will take the cube root of that whole thing. And now let's investigate composing these two. So if I do f of g of x, then, okay, this is f of, and the input is g of x. So it's not x, it's x plus 7 to the 1/3 power. That is what g of x is. And okay, so this is my input. What f does to an input is it cubes it and then it subtracts 7. So I need to cube this quantity. All right, and then I have to subtract 7. And the cube and the cube root, they cancel. And so I get x plus 7 minus 7, which is, of course, just x. And you can check that it also works. If you do g of f of x, you're still just going to get x. All right, so you got to do all the algebra and see that it works. And it should kind of make sense if you think about just reading, doing these actions, and then these actions. If I cube something, then subtract 7, then I add 7, then I cube root it, I've just gone through and undone everything, right? I subtract followed by add, so those cancel. I cube and I cube root, so those cancel. This is the notion of an inverse function in terms of the computational side. Okay, now underneath invertible functions, I have monogamous graphs, which really deserves to be in quotes. Okay, this is just a made-up mnemonic to try and remember what's going on. So let's look at a more abstract notion of a function, which is just an arbitrary pairing. So I have, I guess I'll use x and y. I almost wrote input output, but I'm going to be switching the role of everything. Maybe I should just use a and b, but oh well. So first off, in order to be a function, I would look in the x column or the input column, and if there's ever a repeated input, it had better be paired with the same output, but that would be silly to write. And if there's ever a repeated input with a different output, it's not a function. So okay, now I'm dealing with function. I have different inputs. They go places. Okay, that's fine. And maybe 0 goes to 0. I don't know. So here's a function. And so this is some function f, and if you feed it x, it'll output y. So in other words, f of 1 is 3, f of negative 1 is 2, and f of 0 is 0. Okay. Now, if instead you think of the y column as your input and the x column as your output, this is what would be the inverse function, provided it's actually a function. And when I say provided it's actually a function, let's look at another table. So suppose I have 1, 3 -1, 3, and then still 0, 0. So I just changed one number, and here's x and here's y. And maybe this time this will be a function that I'll call g. Okay? So g is a function, but it's not invertible. When I try to use my y column as an input, what is g of 3? Is g of 3 equal to 1? Is it equal to -1? I don't know, right? Because there's this double pairing with 3 on the right. So this is what I mean by monogamous graphs or monogamous tables. It's just a mnemonic to try and remember what invertible functions are. So I'm going to think of these pairs as like relationships or pairing with partners. And so the pair x equals 1 and y equals 3, they're in a relationship. There you go. But it's not monogamous because y equals 3, you little minx, you are also with x equals -1. Okay? And because it's not monogamous, this is not invertible. I cannot tell you, if you ask me, who is y equals 3's partner? I would say, do you mean who are the partners, plural? And that's why it's not a function, right? It's because I don't know how to define this output. But when there's a pairing where the x and the y pair, there's no repeats with any other numbers, then you have an invertible function. So, subtle point here. I'm not saying numbers cannot repeat in the sense of, let's look at another example, x, y. I'll have 1 and 2, and 2 and 1, and -1 and 7. Okay, now you might look at this and you might say, wait a second, there's a 2 here and there's a 2 here. Let me make it even a little bit more different here. -7 for that too. Okay, you might look at this and you might say, there's a 2 here and there's a 2 here. This is not monogamous. Okay, well, if I was going to continue with this analogy, I don't know if it'll help you remember, but 1 is not the name of this person in the relationship. It's x equals 1. And 2 is not the name. It's y equals 2. So here I have x equals 2. That's a different person than y equals 2. So I actually am still what I would be calling monogamous in this just desperate attempt of a mnemonic to try and remember what's going on. This example here is invertible. It is invertible. It is not ambiguous to go from the right column to the left column. If you give me a number, I can tell you which thing it's paired with. Simply because there's no repeats on the y column. And this is exactly what the horizontal line test is checking. So if I have... Oh, you know what? I actually saved an image just for this, and all that image is a blank thing. All right, great. So if I have some kind of function. Okay, so there in green is my function f. And f is going to fail the horizontal line test, right? Here you go. Boom. It fails it. Nonetheless, if I think about how does someone graph a function, this is something we all know, but sometimes we don't think about explicitly. For some x value, you're going to plot the point. So if x equals a, this will be a comma f of a. All right. Now, if similar to this table up here, instead of thinking of x as my input and y as my output, if I want to think of y as my input and x as my output, I can produce a graph that does that by just switching these pairs, these numbers here. So if instead, this might seem a little weird, but instead of graphing all the points that look like this, if I were to graph all the points that look like f of a comma a, so you know what, here, let's just do it with a explicit example. So consider, what's something that's relatively nice. If I were to do maybe like x squared over 10, and the only reason I'm choosing that is because if I plug in 20, then 20 squared is 400, but over 10 is 40, and so I get to this point right here, which I can do, and I can plot, and okay, so maybe it's something like this, okay? So here's my function, and Okay, I just plotted the point 20 comma 40. So 20 is my input, 40 is my output. Similarly, there's the point negative 20 comma 40. And the way I plot these is I pick a point and then I plug it into my function. Okay, but now if I switch these around, I switch who is x and who is y, then I would have to plot, for example, the point 40 comma 20 and the point 40 comma negative 20. So let's do that. So 40, 20, 40, negative 20, and the inverse graph would look something like this, okay? And in general, the way you get an inverse graph is you reflect your graph over the line y equals x, which is why the dashed line y equals x is here. A reflection corresponds to switching these two entries. So there you have it. The red is my inverse graph, but graph is a much more liberal term than function. The red fails the vertical line test. It's not a function. And if you think about what a reflection does to a vertical line, it becomes a horizontal line, and vice versa. And by a reflection, I mean the reflection along y equals x. So let's look at that for a moment. So for example, the line x equals 60, here it is, x equals 60. It's all the points of numbers that look like 60 comma a. So y can be whatever it wants, but x is 60. And if I switch who's who, then this becomes a comma 60. So now x can be whatever it wants, but y is 60. And that's this line right here. So a vertical became a horizontal, and a horizontal became a vertical. And this is why, if a horizontal line passes through your graph more than once, then the inverse graph is not going to be a function. Okay, however, let's look at one more example, and then we'll call it good. If instead I had a function that is invertible, then when I do the reflection, we get something where the red graph is now indeed a function. It passes the vertical line test. And I knew that ahead of time by looking at horizontal lines on the black graph. So, what is an inverse function technically? It's, well, okay, two functions are inverses if when you do the composition, f of g of x, you'll get x. And it has to work in both ways. G of f of x is x. So, word of caution, it is true that the square root of x squared is equal to x, but it is not true that the square root of x squared is equal to x. This is not true. What it is equal to is the absolute value of x. And you can convince yourself this by plugging in any negative number. So let's use -1, for example. Plug it in, you'll get +1. Okay, so you really do have to check both conditions at times when you're testing it out. I like to say the function in words and notice that they're opposite. So say what the function does. Notice the inverse will do the opposite stuff in the opposite order. And that is exactly why when you do one followed by the other, they'll undo each other. Okay, on a table, the inverse function is the one that takes the right-hand column and outputs the left, whereas the original takes the left-hand column and outputs the right. And then different manifestations of the horizontal line test are essentially just checking for repeats in y values, whether that's on a table or whether that is on a graph. All right, I think that's everything I want to say about inverse functions. So good luck, and I'll see you next time.